So I'll get started right away. Here is a motivating example of a feedback control system, a common enough control system that most of us are familiar with. It's a room heating control system. There's a furnace and which heats the room, and there's a temperature sensor which senses the temperature. If the temperature is higher than the set point, then the fuel flow valve is shut off. Otherwise, it's turned on to heat the room. And here's a block diagram representation of the same system. So block diagram representations are pretty common in control systems analysis and design. There are three. The subsystems are represented by individual blocks. Here the controller is the thermostat, which can either turn on or off depending upon whether the error signal is upon the sign of the error signal, if it is greater than 0 or less than 0. Now it turns out that for many applications such a crude on-off controller may not be sufficient, so different control policy is called for. So here is the kind of a general feedback loop that we will be looking at in this talk. There is the controller and the system to be controlled in the presence of disturbances and sensor noise, and the objective is to generally maintain the output as close to the set point as possible. In particular, we will be looking at a certain type of controller called the PID controller. Now the PID controller, as the name suggests, is a three-term controller. It has got three basic modes: the proportional, integral, and the derivative modes, and they have to be combined in a particular, depending upon what the application is or what the system is. The P, I, and D terms may be combined in a particular fashion, and their values may be computed using particular algorithms to give numbers. And this is the kind of control law that will result finally. The U of t. And in Mathematica, this is a computation of a PID controller is possible using the PID tune function, and it takes as an input the system, a description of the system. In this case, I show a transfer function model, and if we evaluate the model, by default for most cases, the controller obtained from the PID tune function will be a PI controller. We obtain the transfer function description of a PI controller. We can also obtain a PID controller by explicitly specifying the controller type. In this case, we got the transfer function of a PID controller. And if we want to look at the P, I, and D gains or the numbers, a particular form of these can be obtained by calling the PID tune function with the property feedback ideal parameters. We can see that the first one is a PI controller because the derivative term is 0. And for the PID controller, all the three terms are non-zero. Now that you have the controller, we want to test how the controller performs in a closed loop. So first we try what the PI controller in the loop looks, what it does in the loop. So remember that we are trying to get y as close as possible to r. In this case, it's a unit step, a constant 1, and there is no disturbance acting on the system. So we can see that the PI controller in the loop has performed well. The final value of the output is equal to 1, which was the desired value, but there is some offshoot. So let us see if adding a derivative term can help. We can see that adding a derivative term has slightly reduced the overshoot, but otherwise the final values are the same. So the PID controller is good as well as the PI controller, but slight performance improvement. And this can be perhaps seen if the two graphs are plotted in the same plot. And as observed before, the presence of the derivative term has added some damping, or it has bettered the stability, the relative stability of the system. And this can, if we look at some numbers, we can see that the phase margin of the system with the PI controller is about 37 degrees, whereas with the PID controller, the phase margin has improved by about 10 degrees. So far we didn't consider the load disturbance or any disturbance present in the system. Now we do so. We assume that there is a persistent disturbance which is entering the system slightly after, somewhat tau seconds maybe after the simulation has started. And we want to see what happens, what the controller can do. We can see that we can see a little bump when the disturbance enters the system. The disturbance attempts to deviate the output from the set point, but the presence of the controller immediately takes care of the disturbance and does a good job in rejecting the disturbance. So now we look at a physical system. It's a liquid level control system. There are two tanks. The outflow of the first tank, the upper tank, is the inflow to the bottom tank, and there is a constant outlet flow from the bottom tank which drains the fluid, and it's required to control the level of the fluid in the second tank by varying the inlet flow into the first tank. So here is a linearized model of the system, the transfer function description. It's a second order system, we can see, and we want to first see what the closed loop behavior is with the PID controller. So we can see again that the controller, the system with the controller in the loop is able to maintain the specified level. In this case, modeled as in unit step command. But there is some overshoot again. So, and the question is it possible to somehow reduce the overshoot by computing the P, I, and D values using a different computation algorithm or a different tuning rule in the PID parlance? So we specify a particular tuning rule, in this case called the kappa tau tuning rule, and we can see that the performance has improved somewhat. In the graphic, the black line represents the performance with the kappa tau tuning rule, and the overshoot has certainly been reduced substantially, and without sacrificing the settling time and the final value. So what about the control effort? Tracking the control effort or keeping track of the control effort is a good thing to do, or correct thing to do, because we do not want to exceed the physical limits of our actuators. So we can see that the default controller gives a higher peak control value than the specified, the new tuning algorithm. And in this case, we can, the conclusion is that better tuning, better closed loop or tracking performance is accompanied by a lower control effort in general. So now we come to this 2 degree of freedom control structure. It can sometimes happen that the P, I, and D values that we had computed for the controller, or kind of embedded in that controller block here, we do not want to change those values. Maybe they're there for a while and no one wants to touch them. And the question arises: can anything be done to shape or to improve the performance of the system, the tracking performance, without touching those values, and by introducing an extra degree of freedom, so to say? And the answer is yes, it can. And this is what the pre-filter block does here. It has some parameters of its own which can be tuned to perhaps give a better performance of the closed loop system without touching the controller block. So we look at the reference tracking performance of this 2 degree of freedom control system. And we can see that with the 2 degree of freedom controller, the closed loop performance closely matches the one with the kappa tau tuning rule which we specified, the new tuning algorithm. So we can argue that we may not even have to go for a new tuning rule. We may just add the 2nd degree of freedom and get away with it. So what of the control effort? The control effort with the 2 degree of freedom controller is also it's smaller than the default tuning rule. And if we want to look at what that feed-forward filter looks like, we can query its transfer function. It's a 2nd order system. It's a filter like this. Now we come to the final part of my talk, the derivative filtering. We saw that the addition of a derivative term to a PI controller can improve the performance of the loop. But many times it so happens that in the presence of a sensor noise, that the presence of the derivative term can deteriorate the system performance, in the sense that the control signal U is noisy in the presence of M, which is the sensor noise. So what to do? I mean, do we have add the derivative term or not? Because the sensor noises are usually present. So here is a kind of a random sensor noise that we model in this case, which is a pretty typical kind of a sensor noise. And we simulate the system performance with a pure PID controller without the derivative filtering. And we can see that the sensor noise is actually amplified at the control input, which is usually not good, because it involves controller wear and tear and chatter, etc. Eddy currents may be induced in the metallic parts. What about the PIFD controller, the PID controller with the derivative filter? Well, with that, the control signal is smoothened out a lot. However, the trade-off is that the peak control effort is also increased. But this is a part of a trade-off in controls design, and maybe some other tuning rule will also reduce that. And the transfer function of the PID controller with the derivative filter looks like this. It has become proper because the term has been added in the denominator. So in conclusion, we have a selection of controller architectures and tuning rules to choose from, which can be used in offline tuning. And we can also query a list of useful properties to help evaluate the design controller in the closed loop. And we can automatically compute the 2 degree of freedom controller. And we saw how this can help. And but there is also the option of manual tuning if the automatically computed controller does not meet the performance objectives. And there are many other examples, etc., applications in the PID tune reference page, the function reference page, which we hope will be of help. That's all I have. So it's Bob's turn now.
All right. So I'm Bob Sandheinrich, and I'm going to be talking about descriptor systems and time delay systems. So these are 2 extensions that we have made for linear systems that we had in version 8. So before I talk about those 2, I'm just going to give a real quick recap of what we had in version 8. So we had 2 different models for linear systems. We had the state space model and the transfer function model. They both model linear time invariant systems. The state space model is in the time domain. The transfer function model is in the frequency domain. And so what I'm going to be talking about is 2 extensions that we've made so that these can model a greater amount of systems, whole new types of systems. So just a quick example to show you, what we've had. Yes, I do. So the state space model is basically just a holder for differential equations in matrix form. And you can form those from, here we have a second order differential equation for this mass spring damper system. And you can, it can work straight from differential equations and create this guy. And then you can convert it into the frequency domain in a transfer function model like Pradipto was showing you in his talk. So here's the first extension I'm going to talk about is descriptor systems. So on the left we have the types of models that we supported in version 8. And on the right we have the equations for descriptor state space. So we have that E matrix or descriptor matrix that's multiplying the derivative of the state there on the left-hand side. These are also called singular systems or implicit systems. Basically, what this allows you to do is model DAEs. So in addition to having differential equations in your model, you can have algebraic equations. So a lot of times those algebraic equations are constraints in your system. So you can have your differential terms and your constraints all in your model, and you can do all of the things that we like to do with dynamic systems model, connect them together in series and feedback, design controllers, do response tests. Everything you can do, you can work with these descriptor models. You can also model improper transfer functions, and because when you convert those to the time domain, it creates a descriptor model. So here's just to show you how we create a descriptor model. You add a 5th matrix to your list of matrices. So in version 8, we could have only taken these guys. Now you just add that descriptor matrix here, and that's what's that E matrix. So now let's look at a simple example of creating one of these guys. So again, we have a mass spring damper system, but now we have these 2 springs. And if you remember your mechanics classes, it's pretty easy to take those 2 springs, reduce it to a single spring, and get right back where we were with the simple example. But maybe you don't remember exactly how to do that. Maybe all the manipulating equations just sounds like a bad time to you. So now you can take all of your equations and throw them into state space model and just get a descriptor system right away. So here we have an equation for the dynamics of the mass. We have just a kinematic equation. So this is like a constraint that says that the displacement of the 2 springs sums to the displacement of the mass. And we have one saying that the forces between the 2 springs are equal. So you can create your state space model straight from those guys. And you see here we have 4 states. And if you take your time and look at the matrices, you see that it just is giving you this equation here, or all of these equations. All right. So the second extension that we have is time delays. So once again, we've expanded what our differential equations can support. So here, instead of just having the states x of t and the inputs u of t, you have these x of t minus tau and u of t minus tau. So those taus are delays in the system. And we can take these guys in state space model or transfer function models pretty much anywhere in the system, and to work with time delays. So here's just a basic examples of creating time delay systems. So for continuous time transfer functions, the delays are just exponentials. So you can put an exponential right into your transfer function anywhere, and that's modeling a delay. Here we have the exact same system modeled as a state space model. Here the delay is in the output matrix, and we have this systems model delay operator that allows you to model the delay of 3 seconds as an output delay. And when it's typeset, it creates this character. Don't look at that too closely, because this is a prototype build, and it's gonna look different in the real thing. But it'll do the same thing. So now let's look at an example of a time delay system. So here we have a picture of a lathe and a diagram showing that lathe cutting a piece of metal. So here, this equation here is trying to model the position of the very tip of this cutting tool as it cuts. So as it cuts, it creates this what's called a chip. So this piece of metal that's being cut away is called the chip. And the thickness of that chip depends on the position of the cutting tool now and the position the previous rotation of the workpiece. So that creates an inherent delay in the system. So when you go to model the forces on that cutting tool, you end up with this term here, which is x of t minus tau. So tau here is the delay. You also have terms for the stiffness of the cutting tool and the damping in the tool, and the feed rate that you're trying to move the cutting tool at. So we can create a state space model, just like we have the last couple times, and then we're going to immediately convert it to a transfer function model. So here we have our second order transfer function model with this exponential in it to model our delay. And of course, it's all symbolic and nice. One thing you can do to see sort of the interesting ways that these delays affect systems is to create a frequency response. So here we're going to do a Bodie plot. So we're going to plug in some numeric values and create the Bodie plot. And you can see here that we have all these ripples. So that's caused by having that delay in the system. And that's almost certainly an undesirable characteristic of your system. So what you're probably going to want to do if you're making this lathe here is to create a filter to try to eliminate some of those ripples, at least in the magnitude. And one type of filter you can do is a notch filter. So here we have a Butterworth notch filter, which is sort of a standard system. It's a second order system, and it has these two parameters B and Q that we can play with that more or less control the depth of the notch and the width of the notch. So we're going to find values of those, and since we're in Mathematica, we can throw this Bodie plot into a manipulate and play with those values until things look okay. So I don't know, that looks not quite as terrible as the original one. So you could pop these open, and you have your values. So there you've designed a filter so that the lathe isn't so terrible. So now let's look at a second example for time delay systems. So in addition to just sort of the maybe ad hoc controller design that we had there's also specific design techniques for time delay systems. And one of those is called the Smith predictor. It's a very common way of trying to control time delay systems. So here we have our simple first order time delay system that could be I don't know, motor or anything with first order dynamics. And we're going to want to control that with a PI controller. Now we're all experts on PI controllers, so you guys know exactly what's going on there. So we're going to first thing we're going to do is just connect that PI controller with our system and to create our closed loop model and see how it responds. So we're going to create two responses here. The first one, I'm setting the delay to 0, so it's a delay-free system. And the second one, I'm giving it a non-zero value. So let's plot both of those, and you see here's our delay-free response, which is a nice, perfectly regulated response like the ones that Pradipto was trying to create for all of his systems. And here's the second one where we have delay, and you can see it becomes unstable. So having that delay in your system causes big problems. So what the Smith predictor does is it takes your time delay system and the controller that you designed for the delay-free system and gives you a new controller to replace that one that compensates for delays in that system. So the function that we have is Smith delay compensator. That's what gives you the Smith predictor. So it takes, again, our time delay system and the controller that gave us a nice response for the delay-free system, and that gives us our new controller. So here's our new controller that we're replacing the PI controller with. We can go through the same process of creating a closed loop system, and you know that this has worked already because there's no exponentials in the denominator. Exponentials in the denominator are the only things that are going to mess up your stability and give you all sorts of bad things. So we can test that, and we can plot them all together. And you can see here, this blue one, that was the delay-free system. And the Smith predictor one has almost the exact same characteristics. It's just delayed by that 1.5 seconds that we have for our delay. So the Smith predictor is a great thing for working with these time delay systems. In addition to compensating for the delays, another approach is to approximate them. So you can approximate your time delay system with a delay-free system, and then design a controller for that, and then apply that back to your time delay system. So we have the same time delay system here, the same transfer function model that we were working with before, but now instead of using a Smith compensator, and one of the problems with the Smith predictor is if your model is inaccurate, it can make things worse than ever before. So this way might be a little more robust. So what we're going to do is approximate our delays using systems model delay approximate, and we're going to throw some numeric values for our parameters, and then we're going to do a third order approximation of that delay. So this is just calling PID A approximate internally to create a higher order delay-free system that's approximately equivalent to the time delay system. And then once you have your delay-free system, you can use any of the design tools that we have for working with delay-free systems. So here I'm going to use what Pradipto was just talking about, the PID tune, a new function we have to create a PI controller for the approximate system. And then we're going to take that controller and see if, because we know it works for the approximate system, we're going to see if it works for the actual time delay system. So here we have our closed loop system, and now we do have those exponentials in the denominator, so we can't be sure it's going to be any good, but we can simulate it, and there we have a response. So it is stable. It goes to that unit step input. It settles out at 1. So that's pretty good. And the last thing I want to talk about is the case where you have both a descriptor system and a time delay system all together. So when you have both of these things, when you have a descriptor matrix and you have time delays, sometimes what you end up with is called a neutral type delay system. And these things are sort of crazy. There's a lot of work to be done with them research-wise. They have strange characteristics. So I'll just give you an example of so here we have a descriptor, a scalar descriptor state-space model, just as standard as it can come. And we're putting a feedback on that in a controller. So there's a delay in that. So maybe one of your sensors is a little slow to pick up a velocity measurement or something like that. So you end up with this delay in your controller. And so here we have our closed loop system. And this guy is a neutral type time delay system. And we can simulate that. And because our ND solve is so great with all these things. And when you plot that, you get these impulses throughout your response. And that's sort of a common characteristic that you see with these neutral type systems.